In section 3.1, we look at solving systems of equations graphically. Particularly, we are looking at solving systems of linear equations. Remember, linear just means lines. So just a quick review of what it means to graph a line. And here we have the equation of one line, 2x plus 3y equals 12, and I've listed three solutions to this line. So if x equals 0, y equals 4, if x equals 3, y equals 2, and if x equals 6, y equals 0. And each of those points is on the graph. You can see 0, 4 is here, 3, 2 is here, and 6, 0 is a little bit off the screen here. So keep in mind, when you graph a line, or actually when you graph anything, you are graphing the solutions to that equation. So there are many other solutions on this line that are not listed in this table. Our second equation is also a line, y equals 1/3 times x plus 1. And I have listed three of its solutions as well. And you can see these solutions on the graph. 0, 1 is right here. 3, 2 is here. And 6, 3 is a little bit off the picture here. And once again, there are many solutions to this equation, and they are all on this line somewhere. So that's a review of graphing lines, but we're going to be solving systems of equations graphically. So first of all, what is a system of equations? Well, it turns out if you take these two equations and put them together in a single problem, we would get a system of equations. And the solution to the system would be the points that they have in common. In other words, the x and y coordinate that solves both equations. So if I take those same two equations that we just went over and put them together, we now have a system of equations. And if I graph each of those equations simultaneously, here we have the graph of y equals 1/3 x plus 1, and here we have the graph of 2x plus 3y equals 12. You can see that these two lines intersect at this point, and that point has coordinates 3, 2. And that point is the solution to the system. So we would simply write the solution is x equals 3, y equals 2. Now there aren't any other solutions because you can clearly see that this is the only point where these two lines intersect. And so this system has one solution. And when your system has one solution, we say that it is a consistent system and also an independent system. You will see some reference to these words now and again in your homework assignments, but don't spend too much time worrying about this verbiage. It's more important that you simply understand what it means to solve a system of equations. This is the usual case. Now, when I say this is the usual case, what I mean is when solving a system of equations, you will typically get one answer. However, this is not the only possibility. So let's look at some other cases, some other possibilities. So here we have systems of equations, special cases. There are two special cases. One is that if you're graphing two lines, the lines could be parallel to each other. And if they are parallel, then that means they do not intersect. And if they do not intersect, they have no solution, meaning the system of equations would have no solution. And in this case, we call the system inconsistent and independent. Inconsistent simply means there is no solution. The other case is, what if you graphed two lines and they actually ended up being the same line? In this case, you should be able to see very faintly here that there are two lines graphed in the same location. But in this case, there are many solutions. In fact, there are infinitely many solutions because every point on one line is also on the other line. And in this case, we say the system is consistent and dependent. And if you wanted to write the actual solution, we would say the solution is the set of all points x and y such that x and y have to satisfy this equation. And this is the equation of one of those lines. Again, the most important thing to realize here is that when you're solving a system, you get one of three possibilities. One possibility is that you have one solution, and this is by far the most common. The other possibility is that you have no solutions. And the third possibility is you could have infinitely many solutions. But when solving a system of linear equations, it's always one of these three possibilities. Okay, so that basically concludes our initial discussion on solving systems by graphing. Graphing is a very inefficient method for solving systems because graphing is time-consuming, but also graphing can be very inaccurate. It's not very precise. For example, what if two lines intersect, but they intersect at a point which is not clearly whole number coordinates? How would you determine what the point of intersection is? So we need different methods besides graphing. Graphing is a great way to introduce the concepts of systems of equations, but it is not a great method for actually solving problems. So in your homework, the vast majority of problems will not be solved graphically. Instead, they will be solved algebraically. And that's our next section. So in 3.2, we look at solving systems of equations algebraically. There are two methods that we use. One is called the substitution method. And the substitution method basically means that you're going to take one of your two equations, you're going to solve for one of the variables, unless it's already solved for you, like in this case, and then you're going to substitute that expression into the other equation. So let's take a look at how we would solve this system. And by the way, this should look familiar. This is the same system that we looked at in section 3.1. The main principle is, in the second equation, since y is equal to 1/3 x plus 1, we can take that expression, 1/3 x plus 1, and we can substitute it in to replace y in the first equation. Now, when you do that, this first equation becomes 2x plus 3 times y, which is being replaced with 1/3 x plus 1, is equal to 12. And by substituting, notice that what you've done is you've taken that first equation, which used to have two variables, and now it only has one variable. And that means you can solve it for x. So let's go ahead and solve. This is 2x plus, if we distribute, 3 times 1/3 is 1, so we get 1x. plus 3 times 1 is 3 equals 12. Combine like terms, that's 3x plus 3 equals 12. Subtract 3 from both sides, and this gives us 3x is equal to 9. And finally, if we divide both sides by 3, we get x is equal to 3. And x equals 3 is part of our answer. Remember, when solving a system, you are looking for a point of intersection, and a point of intersection has an x-coordinate and a y-coordinate. So once I know x equals 3, I will take the second equation here, which says y equals 1/3 x plus 1, and I'm just going to substitute x equals 3 into there. And when we do that, we get y equals 1/3 times 3 plus 1. 1/3 times 3 is 1, plus 1 equals 2. And so we get y equals 2. And that means the solution here is the point 3, 2. And you'll notice that this is the same result that we got when we graphed those two lines in the previous section. So this is how the substitution method works. And this problem was kind of nice because one of your two equations, particularly the second equation, was already solved for one of your variables. So you have to isolate either x or y when using the substitution method. Let's look at our second example. So in our second example, notice that both equations are in standard form. That means that x or y is not isolated in either equation. So what I'm going to do is solve for either x or y in either the first equation or the second equation. The truth is, it doesn't matter which equation you choose to solve for which variable, but usually there is one variable that is easier to solve for than the others. So in this case, I hope you can see that in the second equation, it's pretty easy to solve for x because all we need to do is subtract 2y from both sides. So let's go ahead and solve for x in the second equation. And so the second equation is x plus 2y equals 8. I'm going to subtract 2y from both sides, and that gives us x is equal to 8 minus 2y. Now our first equation stays the same for now, and we're going to take the expression that we solved for here, and we're going to substitute that into the other equation, replacing the x. And again, we're replacing the x because x is equal to this. So if we know x is equal to something, we can replace x with that expression. So when we make that replacement, we get 3x, no, we don't get 3x, we get 3 times, and what is x equal to? 8 minus 2y, and then minus 4y equals 9. And so you can see that when we replace x with this expression, the resulting equation only has one variable in it, and that means that we can solve for that variable. So if we multiply this out, we get 24 minus 6y minus 4y equals 9. And this is 24 minus 10y is equal to 9. And if we subtract 24 from both sides, we end up getting negative 10y is equal to 9 take away 24 is negative 15. And then dividing both sides by negative 10, we end up getting y equals 3/2. Now, if y equals 3 over 2, we can substitute that back into our original substitution. So what I mean is I'm going to take y equals 3 over 2, and we're going to plug that in to the original substitution that we made, which was right here. So that original substitution was x equals 8 minus 2y. And then we are going to take our answer for y and plug it in. And when doing so, we get x equals 8 minus 2 times 3 over 2, which is 8 minus 2's cancel. So it's 8 minus 3, which is 5. And so x is equal to 5. And that means our solution is the point xy, x is 5, y is 3 over 2. And again, notice that we only have one solution. Okay, so this is the method of substitution. Now we're going to look at a different method, which is sometimes easier to use depending on how the problem is stated. The next method is called the elimination method, and it is also sometimes called the addition method. And the reason it's called elimination is because we are looking to eliminate one of the two variables. And so our first example here, in example number 3, we have two equations of lines. They are both in standard form, which is actually really important. And notice that the x's line up, the y's line up, the equal signs line up, and the numbers line up. And another thing you might notice is that positive 2y and negative 2y are opposites. So if we add these equations together, these will cancel out. They will get eliminated. So what we're going to do to use the elimination method is I'm going to take these two equations and we're going to add them together. And when doing so, these cancel. 5x plus 3x is 8x. 10 plus 6 is 16. And notice that we can now very easily solve for x by simply dividing both sides by 8. So when the elimination method is used on a problem where everything is already set up for you very nicely, it's a really efficient method. Now, we're not quite finished. Once we know what x is, remember, we now have to take that value of x and we have to plug it into one of those two equations. It doesn't matter which equation you plug it into. Let me plug it into the first equation, which is 5x plus 2y equals 10. And if I put x equals 2 into here, that will give us 5 times 2 plus 2y equals 10, which is 10 plus 2y equals 10. If we subtract 10 from both sides, we get 2y is equal to 0. And if we divide by 2 on both sides, we get y equals 0. And so the solution here is the point 2, 0. X equals 2, y equals 0. Now, clearly, this was an easy problem for elimination. And the reason it was easy or simple is because your y's in both equations had opposite numbers in front of them. And that's what made them cancel out when you add them together. This will not always be the case. sometimes you'll have to do additional work to get those things to cancel. Let's consider the next example. So in example 4 here, we have 3/2 x minus 2/3 y equals 0, and 3/4 x plus 4/3 y equals 5/2. Now, before we even consider using the elimination method, it's really important that we clear the fractions here. This problem will be much easier if we don't have any fractions. So what I'm going to do here in the first equation is I'm going to multiply both sides of the equation by the least common denominator. And the least common denominator between 2 and 3 is 6. So I'll multiply both sides by 6. And when we do that, we get 6 times 3/2. Now, what is 6 times 3/2? One way to do that is 6 times 3 is 18, divided by 2 is 9. So that's going to be 6 times 3/2 is 9x minus, then we have to do 6 times 2/3, which is going to be 4, and then y. And on the other side, 6 times 0 is 0. And then I need to clear the fractions in the second equation. So here I'm going to multiply both sides by the least common denominator of 4, 3, and 2, which is 12. And if we multiply here, we get 12 times 3/4, which is 9x, 12 times 4/3, which is 16, and then y, and then 5/2 times 12 is 30. Now what you should notice here in this system, you should notice that the x's are lined up, the y's are lined up, and the numbers are lined up. However, we don't have opposite signs in front of those same coefficients. What I mean is we have a 9x and a 9x. But if you add those together, you don't get 0. You get 18x. So if we want to cancel the x's here, let's say, we need one of these to be negative. So what I'm going to do is I'm going to take that first equation there, and I'm going to multiply both sides by -1. And when we do that, that first equation becomes -9x plus 4y equals 0. And the second equation stays the same. And now you can see that if we add these together, the -9x and the positive 9x will cancel out. And we end up getting 20y equals 30. And then if we divide both sides by 20, we end up with y equals 30 divided by 20 can be reduced to 3/2. Now that's part of our answer. To get the x value of the point of intersection, you have to take your answer for y and you have to plug it into one of the previous equations. And honestly, it can be any one of these previous equations. So I think what I will do is I will take y equals 3/2, and I will plug it into this equation right here. So when we plug that in, we get 9x plus 16 multiplied by y, which is 3/2, equals 30. This is 9x plus 2 goes into 16 8 times, and then 8 times 3 is 24. Subtract 24 from both sides, and divide by 9 on both sides. And we get x equals 6 over 9, which reduces to 2/3. And so the solution here is x equals 2/3, y equals 3/2. And you have to be careful in the end because sometimes students will get these solutions backwards. Remember, x always goes first and y always goes second. Now, substitution can be a little bit more complicated, especially if your x and or your y does not have the same number in front of it. So let's look at one more example. Consider this system. 5x minus 4y equals 10, and 3x plus 5y equals -2. If I want to solve this using elimination, which is the method I'm going to use here, notice that neither the x's nor the y's have the same coefficient in front. So this means, first of all, I need to pick which variable I would like to eliminate. And secondly, I need to get those coefficients in front of that variable to be opposites of each other. Now, you can choose to eliminate either x or y. It doesn't really make any difference. I'm going to choose to eliminate the y. And the reason is because the y variable already has an opposite sign. We have a negative here and a positive here, and we need that for those to cancel. However, we need these numbers to be the same. So to get these numbers to be the same, I'm going to find the least common multiple of 4 and 5, which is 20, and I'm going to turn both of these into 20y. Particularly, we'll have negative 20y here and positive 20y here. So to change -4 into -20, we need to take that equation and multiply both sides by 5. If we do that, that equation will turn into 25x minus 20y equals 50. So you can see we got our -20y that we wanted, but you should also see that the x and the number here also changed. Now in the second equation, we're going to turn this positive 5y into a positive 20y. And to do that, we need to multiply both sides of this equation by 4. And if we do that multiplication, we get 12x plus 20y is equal to -8. And now you can see that we can add these equations together because -20y and positive 20y will cancel out. And when you do this, you get 37x is equal to 50 minus 8 is 42. Then we divide both sides by 37, and we get x equals 42 over 37. Now, when you first get an answer like this, I think the most common reaction is, I must have done something wrong. But the truth is, sometimes answers are complicated like this. So once we know what x is, we now need to figure out what does y equal. And so to do that, I'm going to substitute the value of x into one of the two equations. And I'm going to choose to plug it into the second equation. Here's the second equation. I'm going to put x equals 42 over 37 into here. And when we do that, we get 3 times 42 over 37 plus 5 times y equals -2. 3 is like 3 over 1. So 3 times 42 is 126 over 37 plus 5y equals -2. And then I'm going to subtract 126 over 37 from both sides. This gives us 5y is equal to negative 2 minus 126 over 37. Okay, so at this point you might be thinking, well, this is getting a little bit ridiculous. And I guess I would partially agree, but this is just arithmetic. And you can get a common denominator to subtract these numbers, or you can use a calculator. But whatever you do, keep your answer in fraction form. Try not to give a decimal equivalent because sometimes decimal answers are not exactly correct. Now I'm going to go through and show all steps. So I'm going to think of negative 2 as negative 2 over 1. I'm going to multiply the top and bottom by 37 to get a common denominator. This will give us negative 74 over 37 minus 126 over 37. And now we just need to subtract negative 74 minus 126. And if you do that, you get negative 200 over the common denominator, which is 37. And then to finish this up, I'm going to get rid of the 5 by multiplying both sides by 1/5. This will cancel the 5s here and give us y equals, and this is negative 40 over 37 because 5 goes into 240 times. And so here's our value for y. And so our solution, remember, is a point. And the point for this one is x equals 42 over 37, y equals negative 40 over 37. And this is our answer. Now, if I'm being truthful with you, you will rarely get answers that are this complicated with fractions that have denominators such as 37. But it is a possibility, and you shouldn't be afraid of these problems. You should just know how to deal with these sort of complicated fractions. Okay, we're going to look at 2 more examples. These last 2 examples are how do you identify when you have either parallel lines or lines that are actually the same line. So we're going to talk about our special cases. So in example 6, notice that you have your system of equations here, and things are not particularly well organized. Well, that doesn't really matter. You could simplify things if you want, or you could simply make the substitution x equals 14 minus 2y and just plug it in for both x's. My recommendation would be to go ahead and simplify the first equation. You don't have to do this, but if you do, that first equation will become 2x plus 2y equals x plus 12. And then if we subtract x from both sides, this will give us x plus 2y equals 12. Now I can take my second equation, x equals 14 minus 2y, and we can replace the x in the first equation with that expression 14 minus 2y. And when we do that, we end up with this equation. And of course, what happens here is these cancel out, right? Negative 2y and positive 2y cancel out, and we get 14 equals 12. So this is a special case. Notice that your variable completely canceled. There's nothing to solve for. And notice that this is a false statement. 14 is in fact not the same as 12. And this is indicating that this system has no solution. And graphically, what that means is that you have parallel lines. But again, we don't need to really be concerned too much about the graph. It's just the simple fact that algebraically this has no solution. For example 7, we have a system which is very similar to the last one in that both of these could use some rewriting, some simplification. So this first equation, if we multiply it out, we get 3x equals 12 minus 2y. And if we add 2y to both sides, we end up getting 3x plus 2y equals 12. The second equation, if we multiply it out, we get 2y equals 12 minus 3x. And if we add 3x to both sides, we get 3x plus 2y equals 12. And what you should notice as a system is that these two equations are exactly the same. That means that if you graph these, you have the same line. And what that means is that this system has infinitely many solutions. And the way you can represent that answer is the solutions to this system is a set of all points x and y such that 3x plus 2y must be equal to 12. And essentially what you're saying here is the solution is all the points on the line. And I say the line because there's actually two lines here, but they are the same line when you graph them. Now, if you didn't recognize that right away, of course, you could have taken those two equations, which they're the same, so it looks a little strange here. And if you multiplied one of those equations by -1, then what you would get is 3x plus 2y equals 12 for the first equation, and -3x minus 2y is -12 for the second equation. And if you add those together, you end up getting 0 equals 0. And so another way that you can sometimes recognize when you have infinitely many solutions is when you end up with a true statement like 0 equals 0, or you might have something like 5 equals 5, etc. Okay, so this is a brief introduction to solving systems of equations, both graphically and algebraically. Time to do some homework.